The single-layer perceptron. I mean, it was revolutionary for its time, but its function was surprisingly simple, right?
Oh, incredibly simple. Conceptually, it was trying to mimic a basic biological neuron. It takes a bunch of real valued inputs, x1 through xn,
Right.
and it assigns a weight, a wi, to each one. And that weight just represents the strength of that connection.
So it's like a little volume knob for each input.
Exactly. Then it just does a weighted sum, a linear combination of those inputs and weights. And it adds a bias term, W0.
And that bias term, which is often just treated as another weight connected to an input that's always set to 1, that's basically the trigger point, the threshold.
Precisely. The output is a simple binary choice. 1, if that weighted sum goes over the threshold, and 0 if it doesn't.
Geometrically, that's just a straight line.
A single straight line or, a flat plane, a hyperplane in higher dimensions, it just divides the input space in two. A digital switch making a linear decision.
And that right there, that was its crippling weakness. The failure that basically stopped the entire field of neural networks dead in its tracks for years.
The infamous XOR problem.
The XOR problem.
Yeah, and the XOR, or exclusive OR function is, it's so deceptively simple. If the inputs are the same, like 0, 0, or 1, 1, the output is 0.
Okay.
If they're different, 0, 1, or 1, 0, the output is 1.
Right.
The problem is, if you plot those 4 points on a simple two-dimensional graph, you cannot draw a single straight line to cleanly separate the two classes.
You can't separate the ones from the zeros with one cut.
Impossible. And this means the single-layer perceptron is fundamentally limited. It can only classify what we call linearly separable functions.
For everything else, even something as basic as XOR, the model was just useless.
Yeah, and it wasn't about cleverness or more data. It was a theoretical and architectural limit.
So the challenge became, how do you build a network that can handle functions that need nonlinear boundaries? How do you let it curve and twist its decision surface?
And that, of course, is what leads us directly to the solution.
The multilayer perceptron.
The multilayer perceptron, the structural fix. The name really says it all.
Right.
It is a network defined by having one or more layers of neurons that are hidden.
Hidden from both the external inputs and the final output.
Right.
And the key insight here, the big idea, is that these hidden layers aren't just redundant. They're doing intermediate processing steps that let the network transform the geometry of the problem itself.
That's a great way to put it. It's like you're adding extra spatial dimensions to the data so you can untangle it.
Yeah.
Exactly. This layered sequential processing gives the MLP the flexibility it needs to define those complex, non-linearly separable patterns. It's not just drawing straight lines anymore.
It's drawing curves and elaborate boundaries and high dimensions.
Yes. For an MLP to function as a modern learner, especially when you think about the math of backpropagation, it has to have 3 essential features.
Okay, what are they?
The first, and this is arguably the most critical feature, is the need for a nonlinear activation function for each neuron.
Okay, not just a simple on-off switch.
No. And what's more, this activation function has to be differentiable. If we stick with that old perceptron step function, the one that jumps instantly from 0 to 1,
You can't do the calculus.
you can't do the calculus required for learning.
Yeah.
And we'll spend a lot of time on why that differentiability is absolutely non-negotiable when we talk about propagating error.
Okay, so that's 1. What's 2?
Feature 2 is, well, it's obvious, but it's fundamental. The presence of hidden layers. These layers are the real workhorses. They aren't just relaying information, they are manipulating it.
They're shielded from the outside world, just doing that essential feature transformation.
Exactly. And feature 3, high connectivity. MLPs are typically fully connected.
Meaning every neuron in one layer talks to every neuron in the next layer.
Right. And this high degree of connectivity, which is defined by all those synaptic weights, the WMOs, it ensures information flows freely. It lets the network consider all the possible relationships between inputs and features.
Okay, let's break down those layers visually. We start at the bottom with the input layer.
The input layer is passive. It's just an interface. It accepts the raw data pixels, numbers, whatever the problem is, and just introduces them into the system.
But no processing happens there, no math.
No math at all, no weighted sums, no activation functions. It's just the front door.
Then we hit the hidden layers. You called them the workhorses. What exactly are they doing in there?
Their primary role, and this is profound, is the classification and abstraction of features.
Okay, what does that mean in practice?
Think of it this way. If you feed an image of a cat into the network, the first hidden layer might learn to detect really simple things, like edges and lines.
Yeah.
The next hidden layer might take those lines and combine them into shapes like ears or eyes or whiskers. They are building up a hierarchical representation of the data.
So this feature abstraction is the source of the MLP's power. It's fascinating, though, that the theoretical requirement for how many layers you need is, well, it's surprisingly small.
Yes, a theory is really powerful here. 2 hidden layers are sufficient to solve any problem. That's a key result in approximation theory.
But modern deep learning networks use dozens, even hundreds of layers. If 2 is enough, why bother?
Because theoretical sufficiency often clashes with practical efficiency. More layers, while not strictly required for universal approximation, might just make the learning process faster or capture more fine-grained features.
So depth allows for a more efficient representation.
Exactly. Instead of forcing 2 massive layers to learn incredibly complex mappings, you distribute that complexity over many shallower layers. It actually makes the optimization problem, the learning itself, easier to solve in practice.
That makes a lot of sense. And then finally, we get to the output layer.
The output neurons, they behave functionally like hidden neurons. They do the math, they apply an activation function, but their result is the final answer.
Yeah.
The thing that gets passed out of the network.
And this is where we measure the difference between what the network thought the answer was and what it actually was.
Right. And this whole layered structure dictates 2 fundamental types of signal flow.
The forward pass and the backward pass.
First, the function signals, or the forward pass.
Mm-hmm.
This is the standard operational mode. The input just propagates forward layer by layer until the final result emerges as the network's prediction. That's the active inference.
Okay, and second.
Second, the error signals, the backward pass. And this is purely for learning. The error signal starts at the output layer, where you compare the prediction to the target, and then it propagates backward, layer by layer, flowing in the opposite direction.
And that backward flow is the absolute core of the training mechanism we're about to get into.
It is. Without an efficient way to send that error signal back through those hidden layers, the MLP is just an expensive random guess generator.
Okay, let's dedicate some serious time to this concept of feature detection, because this feels like the fundamental intellectual leap. This is what lets MLPs solve XOR and everything beyond.
Absolutely. Think of those hidden neurons not as simple switches, but as highly specialized trainable feature detectors. Their job is to look at the raw input, the thousands of pixels in an image, and distill that down into something more meaningful.
So, if the original input data space is just a jumbled mess where the classes overlap, what does the network actually do?
The learning process, by adjusting the weights going into those hidden neurons, lets the network discover the salient features of the training data. This whole process is essentially a nonlinear transformation on that input data.
Let's make that more tangible. Imagine you've got a cluster of blue dots and red dots on a 2D plane, but they're intertwined like a spiral.
Right. A single line can't separate them. That's the XOR problem, just in 2D.
So what does the network do?
Okay, so imagine those hidden neurons are applying a really complex mathematical function, a nonlinear twist or a fold, to that 2D space. That complex transformation moves the data into a new, higher dimensional place that we call the feature space.
And the aha moment is that in this new transformed feature space, which the network itself discovered, the red dots and blue dots are suddenly cleanly separated.
Exactly. They might be separated by a simple flat plane in like 50 dimensions, even though they look tangled in 2D.
That is the profound distinction. The MLP isn't just learning where to draw a line in the input space.
No, it's learning how to define a new space where the classes are inherently more easily separated than they were in the original data. This supervised learning process transforms complexity into linearity.
And linearity is all the final output layer needs to function.
Exactly.
That conceptual understanding is so critical. Now, let's see how that feature space translates back into a useful output, which it depends on the task, right?
Right. We have 2 main configurations for the output layer. The first is for regression tasks.
Regression is when you're predicting a continuous number, like a house price or temperature.
For those tasks, the output layer is usually just a single node. And the key point is that the final calculation, that linear combination coming from the last hidden layer, is not put through an activation function.
You just output the raw number?
You output the raw number. If you want to predict 15.7, you output 15.7.
Right, because if you used a sigmoid or a 10 function, it would just squash that value between 0 and 1, or minus 1 and 1, which you definitely don't want.
Exactly. The network needs the full range of real numbers.
And the other configuration is for classification tasks, which are probably more common for these kinds of MLPs.
Yeah, for sure. Classification requires one neuron for every class the network has to distinguish. So if it's identifying 10 types of animals, you need 10 output nodes.
And to manage the targets, we use a standard trick called one-hot encoding.
Right, one-hot encoding is just a simple way to convert a category label, like class 3, into a binary vector. So the position for 3 has a 1, and everything else is 0.
It gives the network a clear numerical target to aim for.
It does. And when you have these multiple classification outputs, the standard choice for the activation function is the softmax activation function.
This is so important for turning raw output scores into something meaningful.
It is. It turns them into probabilities. Softmax is defined mathematically by taking e to the power of the output score for neuron I.
So e to the xi.
And dividing it by the sum of e to the power of all the output scores.
Why that formula? Why the exponentiation?
It does two crucial things. First, it makes sure all the outputs are positive. But second, by taking that ratio, it forces the entire output vector to be a vector of probabilities that sum to exactly 1.
So instead of seeing that neuron 7 has a raw score of 4.5 and neuron 3 has a score of 3.1, softmax tells you, I am 85% sure this is class 7, 10% sure it's class 3, and 5% sure it's everything else combined. You get the network's confidence level.
Precisely. And the input is then classified as whichever class has the highest probability. It's a very intuitive and mathematically consistent output.
And moving back to the hidden layers, that choice of activation function there is also pivotal because we have to have that differentiability.
Right. We talked about the common examples, the old step function, which is now useless for training, the sigmoid, and the ton. For hidden layers, sigmoid or ton are the classic workhorses.
The standard sigmoid function, that's the one that looks like an S-curve, right?
That's the one. It was historically famous because it's a convenient, computationally efficient replacement for the step function. It smoothly squashes any real number into the range between 0 and 1, and its derivative is, well, it's mathematically elegant, which is crucial for backpropagation.
And ton is similar.
Very similar look, but it maps inputs into the range of -1 to 1. It's centered around 0, which, as we'll see, often helps speed up training a bit compared to the standard sigmoid.
Okay, so the takeaway here is MLPs work because hidden layers transform the problem space nonlinearly, and the activation functions make sure that transformation is smooth, continuous, and therefore mathematically trainable.
You've got it. That's the core idea.
Now that we have the architecture and the functions, we can move to the central challenge, training. The ultimate goal is to find the set of weights, the WIJs, that results in the lowest possible prediction error.
So we have to minimize some measure of error.
But before we can minimize it, we have to define exactly what error means in a way we can quantify, which brings us to a crucial metric, mean square error, or MSE.
Let's start with just an instantaneous measurement. For a single training example, let's call it N, and a single output neuron, IJ, the instantaneous error signal is just defined as DJ of N minus YJ of N.
The desired response minus the actual signal, what we wanted minus what we got. Simple subtraction. But we want a total error for the whole network on that one example. This is the instantaneous error energy, which we call E of N.
Okay.
We calculate this by summing up the square of those individual errors across all the output neurons, and we multiply it by 1/2.
So E of Fn equals 1/2 times the sum of EJ squared. Why the squared term and why the 1/2? The squaring I get, it makes everything positive.
The squaring is essential, yeah. We don't care if we were too high or too low, just how far off we were. And it also has a nice side effect of penalizing big errors much more aggressively than small ones.
It makes the network fix its biggest mistakes first.
Right.
But the 1/2, that always seemed a bit random to me. Is it just for mathematical neatness?
Honestly, yes. When we get to gradient descent, we have to take the derivative of this error function. And the derivative of x squared is 2x.
So the 2 cancels out the 1/2.
2 cancels out the 1/2. It's an algebraic trick to keep the calculus clean and avoid carrying around a constant factor in all the final equations. That's a great explanation. Okay, so EON is just for one example. We need a cost function that covers the entire data set in.
That's where the average error energy, or what's sometimes called the empirical risk, comes in. This is the metric we actually want to minimize. It's just the average of that instantaneous error energy across all N training examples.
So this average error is now a single number that tells us how good or bad the network is. It's the target we're trying to drive down to 0.
And crucially, this average error is a function of all the adjustable synaptic weights in the entire network. Finding the minimum of this function is the same as finding the best possible set of weights.
So how do we decide when to adjust those weights based on the error? Two main methods, batch and online learning.
Right, let's contrast them. We can start with batch learning. In this setup, the network calculates the error and the gradient for every single training example,
Every single one.
but it only performs the weight adjustment after it has processed all n examples. That whole cycle is called one epoch.
So you gather up all the information about the error across the entire data set before you do anything.
Yes. The cost function you're minimizing is the true average error energy. And the big advantage is stability. By averaging everything, you get a really accurate estimation of the gradient vector.
So the move you make is very precise.
Very precise. It guarantees convergence to a local minimum under the right conditions. Plus, modern hardware, GPUs, they love batch processing because you can parallelize it efficiently.
But the drawback seems obvious. If your data set N is massive, like billions of examples, one epoch could take days or weeks before you make a single adjustment.
It's computationally prohibitive.
Exactly.
Which leads us to online learning. This operates on an example-by-example basis.
Okay.
You show it one example, calculate the instantaneous error E of n, immediately figure out the weight adjustments, apply them, and then you move right on to the next example.
So the network is constantly jittering and adjusting its weights based on the very last thing it saw.
Which makes the search in weight space stochastic. It's noisy, but it's fast. It's minimizing the total instantaneous error energy. It's hugely popular because it's simple, it's less demanding per update, and it's great for redundant data.
Right. If you have 10,000 nearly identical pictures of a cat, you don't need to average all of them before you start learning. The first few give you a good idea.
Exactly. And because it adjusts so often, it can potentially adapt to data that's changing slightly over time.
So the trade-off is noise versus accuracy.
That's it. Online learning might take a slightly wrong step because it's only looking at one data point, but it takes that step immediately. Batch learning takes a perfectly calculated step, but you might wait a long, long time to do it.
And for big data sets, online learning, or I guess the hybrid mini-batch learning, is pretty much the standard.
It is. It's the practical choice.
So whether we choose batch or online, the underlying engine that's driving the weight changes is the same. Gradient descent.
Gradient descent is the optimization algorithm we use to navigate that high-dimensional error surface, defined by our error function, E of W.
Okay, this is where the mountain range analogy comes in, right?
It's the best one. Picture the error function as this vast, complex landscape. Every point on that landscape is a different combination of all the network's weights, and the height of that point is the error value.
And we're standing somewhere randomly on this mountain range, and we're blindfolded. Our goal is to find the lowest valley, the minimum error.
So since you're blindfolded, how do you know which way to go?
You feel the ground around you.
Exactly. You use the gradient. The gradient is a vector of partial derivatives, and it literally points in the direction of the steepest descent, the direction of increasing error.
But we want to go down to minimize the error, so we move in the exact opposite direction.
Precisely. We approach a local minimum by taking steps that are proportional to the negative of the function's gradient. Those partial derivatives, the ones that make up the gradient, they tell us exactly how much the error will change if we just tweak a specific weight a tiny bit.
So it tells you the most effective direction for error reduction.
That's right. So we compute the gradient vector for all the weights, and then we change each weight by a small amount in the negative direction of that gradient.
And that movement, that delta, is proportional to the negative of the gradient.
And the crucial proportionality constant there is the learning rate, ENA. That's the size of the stride we take. We just keep iterating, calculate the gradient, take a step, recalculate until we've arrived at the bottom.
This whole mathematical framework is formalized in what's called the delta rule.
The delta rule is the weight update mechanism for supervised learning when you're using a differentiable activation function. The math is simple. The new weight is just the old weight plus eta times delta times x.
Where delta is the error term for that neuron, and x is the input signal. This looks a lot like the old perceptron update rule. What makes the delta rule so much more powerful?
Two crucial differences we've sort of touched on. First, the error term, delta, is a continuous real value. It's not just 0, 1, or -1. The network can say, I was slightly wrong, not just I was catastrophically wrong.
Okay.
And second, and this is the pivotal concept that leads us into backpropagation, the delta rule requires a differentiable activation function. This is because calculating that delta term for the output layer involves The derivative of the activation function. It scales the update based on the neuron sensitivity.
And here's the problem that haunted those early researchers, right?
This is it.
The delta rule works perfectly for the output layer, where we have the target answer. We know what it should have been, but how do you adjust the weights in the hidden layer?
Exactly. The moment you go one layer back, the outside world doesn't give you a right answer for that hidden neuron. There is no specified target response.
We have a known error at the very end, but we don't know who in the middle is to blame.
We can't calculate a local delta for a hidden neuron if we don't know what its target, its E star, was supposed to be. This is the credit assignment problem. And solving it is the absolute genius of backpropagation.
So that's the million-dollar question, assigning the blame.
The revolutionary solution to that credit assignment problem needed two things: the right choice of activation function and a brilliant application of basic calculus.
So let's start with the function. We have to replace that non-differentiable step function.
We absolutely have to. And as we mentioned, the sigmoid function is the historically pivotal choice. It's that smooth S-curve.
Right, and it gives us that smooth transition and lets us calculate the derivative, which is the slope of the curve at any point.
Exactly. And when the neuron is highly saturated, the output is close to 0 or 1, the slope is nearly flat, the derivative is near 0.
But if the neuron's in the middle, near 0.5, the slope is steep and the derivative is high.
And that derivative value is critical because it tells us how sensitive is this neuron to changes in its input. If it's already saturated with a flat slope, changing its weights won't affect the output much, so we shouldn't change them very much.
But if it's on that steep part of the curve, it's highly sensitive, and small weight changes will have a big impact.
Right, but the real computational breakthrough of the sigmoid is in the simplicity of its derivative. The derivative, f prime of x, is just f of x times 1 minus f of x.
That is staggering. You don't need some complex exponential calculation to find the derivative.
No.
You only need the output of the neuron itself.
Exactly. This one property made the calculations efficient enough to be practical decades ago. It allowed backpropagation to spread that error signal through the network without massive computational overhead. Without a simple, self-referential derivative like this, backprop would just stay a theoretical curiosity.
Okay, so we have the differentiable neuron. We've established that learning with hidden units is basically learning features. Now, what about the setup before we start training?
The initial step is so crucial. Initializing the weights. The weights have to start as small random values. You typically draw them from a small uniform distribution around 0 or a small Gaussian distribution.
This step sounds trivial, but as we noted, it comes with a dire warning.
It's the symmetry breaking problem. If all the weights start off exactly the same,
They'll all learn the same thing.
every hidden unit gets the same input, calculates the same sum, produces the same output, and, most critically, the error signal propagating back will be identical for all of them.
And if the error is identical, they all update their weights identically.
Which means they will all end up performing the exact same operation and learning the exact same feature. The network just collapses into a single, less powerful unit. It completely fails to use the power of having multiple, diverse feature detectors.
So random weight initialization is essential to break that symmetry.
You have to do it.
With the architecture set and the weights randomized, we can finally launch the backpropagation algorithm.
Backpropagation is an iterative, supervised gradient algorithm. It's designed specifically to minimize that mean square error by efficiently distributing the blame across all the weights in the MLP.
Okay, let's follow that error signal backwards, step by step. This is the heart of the deep dive.
The process starts with a forward pass, which generates our output, y. We calculate the raw error, target minus y. This takes us to the start of the backward pass. We need to calculate that localized error term, that delta, for every neuron K in the output layer.
This is the output layer calculation, and it's based on the delta rule we just discussed.
Right. So delta K is just the error, y star minus y, multiplied by the derivative of the activation function at that neuron.
It scales the error, so we only update weights in proportion to how sensitive that output neuron is.
Exactly. Now for the conceptual jump. How do we calculate the error term for a hidden node, J, which is one layer back?
This is where it gets its name.
This is where backpropagation lives up to its name. The algorithm calculates an effective error term for that hidden node in J by reusing the errors it already calculated in the layer above it.
This is the recursive assignment of blame.
It is. The hidden node calculation for delta J is defined as the derivative of its activation function, f prime of zj, times a summation.
And that summation is the key.
That summation is the sum of the errors, the delta K's, from all the neurons in the next layer, each multiplied by the weight, wjk, that connects our hidden node j to that output node k.
This is the chain rule from calculus, but structured brilliantly. To find out how much hidden node j contributed to the total error.
You look at the errors in the output layer, and you trace them back through the connection weights. If node j has a really strong connection to an output node k that had a huge error, then j gets a large share of the blame, scaled by that weight.
So backpropagation is literally propagating the output error backward, assigning responsibility for that error among the preceding hidden units based on the strength of their influence on the output.
And just like in the output layer, that calculated sum of blame is then multiplied by the derivative of the activation function for the hidden neuron. Again, scaling the blame by the neuron's sensitivity to change.
And once we have all the delta values for the output layer, and then recursively for all the hidden layers, we just plug those back into our weight update rule for every single connection.
That's it. That whole process forward pass, error calculation, backward pass, weight update is one iteration, one step of gradient descent. It's highly efficient. It's highly localized.
Each neuron only needs to know about its own input and the errors from the layer right after it.
Right. And allows the entire network, including those crucial hidden feature detectors, to learn all at the same time.
The ability of backpropagation to train an MLP fundamentally answered the question of how to build a learning machine. Now we can move to the question of what that machine is capable of.
And the representation power of MLPs is one of the most significant theoretical findings in the history of the whole field.
So starting small, back in the Boolean world,
every single Boolean function, and or, not eat, and yes, XOR, can be represented by a two-layer network, one hidden layer. This is the proof that the MLP overcomes that original limitation.
Okay, moving to continuous math, what about continuous functions?
Any continuous function, no matter how complex its shape, can be approximated with arbitrarily small error by a two-layer network, as long as the hidden units use something like a sigmoid or tan, and the output unit is linear.
That's a very strong statement about their modeling capacity.
It is. And finally, the ultimate representation power.
What's that?
The universal approximation theorem extends this. Any arbitrary function, continuous or not, can be approximated to any desired accuracy by a three-layer network. Two hidden layers.
So you're telling me a three-layer network can approximate anything? That's kind of mind-blowing.
Theoretically, yes. Which tells you that any failure we see in AI today is generally not a limit of the architecture's ability to represent the answer. It's a failure of data or optimization or efficiency.
Which brings us right to the practical challenges of training and convergence. An epoch is one full pass through all the training examples. We run this for many, many epochs.
Hoping to stop when the network's outputs match the targets and the weight changes, the delta domes are basically zero.
Right. And with the complex nonlinear MLPs, while convergence is generally guaranteed mathematically, finding the best solution often comes down to tuning the practical parameters.
And there's no more critical parameter to tune than the learning rate, eta. This is the tightrope walk of optimization.
Why is it so hard to pick the right eta?
Because the optimal value is so dependent on the specific problem, the dataset size, the network architecture. You have to experiment wildly. Values can go from 1.0 all the way down to 0.0001.
And the choice is constrained by two opposing catastrophic scenarios.
Right. Scenario 1, eta is too small.
The slow crawl.
The slow crawl that never ends. If the learning rate is minuscule, the network takes these tiny baby steps across the error landscape. Convergence takes an extraordinarily long time, potentially days or weeks longer than it needs to.
In a business sense, you're just burning computing cycles.
Exactly. Scenario 2. Eta is too large. This is the more immediate catastrophe.
Okay.
If the step size is too big, the weight updates will overshoot the error minimum. Imagine standing in a small valley and trying to take a step toward the bottom, but your stride is so large, you leap completely over the minimum and end up halfway up the next mountain.
The weights just diverge, bouncing all over the place, and the error goes up instead of down.
It can explode. The algorithm just fails entirely.
So you need that sweet spot. Large enough for efficient progress, but small enough to settle into the minimum.
Absolutely. And the activation function choice also plays into this. We noted that tan is antisymmetric, while the standard sigmoid isn't. Using an antisymmetric function often leads to faster convergence because the derivatives are generally larger, letting the error signal propagate more effectively.
Okay, so how do you know when to stop? When is the training done?
Well, there are two standard stopping criteria. Since convergence means finding a point where the slope is flat, the mathematical criterion is tied to that gradient vector.
Right. At the minimum, the gradient should be 0.
So the algorithm has converged when the Euclidean norm of the gradient vector reaches a sufficiently small threshold.
Okay, let's translate Euclidean norm of the gradient vector.
Think of it as just the length of the gradient vector. If the length is very close to 0, it means the uphill slope in every direction is virtually flat. We stop training because we're sitting in a flat basin, a minimum.
No more downhill to go.
Exactly. The second, more intuitive criterion is just based on the rate of improvement. Convergence is reached when the absolute rate of change in the average squared error from one epoch to the next is really small. The standard threshold is usually between, say, 0.1% to 1% per epoch.
So if the performance isn't getting any better, you've probably converged, and continuing just risks overfitting or wasting time.
Exactly.
Despite all these mechanisms, standard backprop using simple gradient descent has some pretty significant acknowledged disadvantages.
Oh, yeah. It's inherently slow and inefficient compared to more advanced techniques we have now. It can require tens of thousands of epochs to find a stable solution. But the most critical disadvantage is that it can get stuck in local minima.
A local minimum is a small valley that looks like the lowest point when you're in it, but a deeper, true global minimum exists somewhere else on the landscape.
Exactly. And because gradient descent is a purely local method, it only looks at the direction immediately downhill. If it falls into a local minimum, it gets trapped. It thinks it's done.
And you end up with a suboptimal solution.
And the initial random weights heavily influence which valley you end up falling into.
So we have this powerful but slow, sometimes short-sighted algorithm. How did researchers immediately try to improve it?
By adding momentum. Momentum is this brilliant, physically inspired mechanism designed to help the optimization process overcome small bumps and shallow local minima. It often finds a better minimum in far fewer steps.
The mechanism is conceptually simple, right? It just adds a percentage alpha of the last movement to the current movement. It's like inertia.
Think of a bowling ball rolling down that air surface. Standard gradient descent is like placing the ball and letting it roll one step. If it hits a tiny bump, it stops.
Right.
With momentum, the ball carries forward some of the speed it built up from the previous step. If it encounters a small local minimum or a flat plateau, the inertia lets it slide right over that impediment and continue its journey toward a deeper valley.
So the equation just adds a new term to the update rule. Alpha times the previous weight change.
That's it. That's the historical memory of the previous step. Alpha is usually a small fraction like 0.5 or 0.9. It gives the weight updates history, and it dampens those chaotic movements you get with a really large learning rate.
But the sources are careful to issue a clear warning here.
Yes, and it's an important one. While momentum dramatically improves the efficiency and the effectiveness of the search, adding momentum does not guarantee global minimization.
It doesn't solve the local minima problem entirely.
Not at all. The weight updates are still following the negative gradient. They're just doing it with a smoother, more efficient trajectory. The fundamental trap of local minima is still a possibility.
This deep dive has traveled all the way from the historical failure of the linear perceptron to the computational elegance of backpropagation. We've seen that the MLP's power to solve basically all classification problems rests on two connected pillars.
Structural layering for that nonlinear feature transformation.
And a differentiable training mechanism that efficiently distributes blame using the chain rule.
It's a synthesis of architecture and optimization. We've established that the theoretical representation power of MLPs is immense. Even 3 layers can model any arbitrary function.
So the bottleneck isn't the ability to represent the solution.
No, it's the efficiency and the reliability of the optimization process. That long, slow walk of gradient descent.
Which brings us back to our initial setup and a question for you, the listener, to mull over. If we know, based on these universal approximation theorems, that a surprisingly shallow network can theoretically approximate any complex function, what does this imply about the fundamental limits of what we can model if we just add more layers, more depth, and more data?
If the limitation is no longer theoretical representation, but solely optimization, if it's about improving the speed and stability of that gradient descent process, getting past local minima, better controlling the learning rate, what new, seemingly unsolvable computational problems might we crack simply by improving the tools we use to train these machines?
The theoretical power is already there. The next frontier is making that power practical and instantaneous.
If the math works, the modeling power is unlimited.
A fascinating thought to end on.
Indeed.
Thank you for joining us for the deep dive. We look forward to exploring the next frontier with you soon.